The new PlayStation just came in stock and you want it. They only have a limited quantity, so you really have to buy it immediately. Behind the scenes, there are a bunch of servers and a database cluster which contains a table, storing the inventory. The value is 2, which means only 2 of them are left. So on the product page, you will see this item in stock. So you add it to the cart and try to place the order. But the moment you do that, you see a message that this item has gone out of stock. The last of the 2 quantities have been taken by someone else. But when you go back to the product page, you somehow still see the console available in stock. But how? Did it come back in stock? Or you are seeing stale information? Let's try to answer this question. Behind the scenes, you have a primary database which handles all your writes, and the read replicas which handle all the reads. Whenever something is written to the primary, it is pushed to the read replicas. The last 2 units are consistent and present in all the replicas. But suddenly there is a network issue and the connection between primary and the read replicas break. They all are still connected to the internet and are accessible, but the primary cannot push updates to the read replicas. In this moment, if a person purchases 2 quantities, the primary database would be updated, making the inventory 0. But the read replicas still show the inventory as 2. At this point, if you go to the product page, you would still see the item in stock, which is stale data. However, when you add the item to the cart and try to place the order, the database transaction, which also involves updating the inventory, goes to the primary replica and fails because it attempts to make the inventory go below 0, which is not allowed. Now, although we understand this problem, do we actually want this kind of behavior? That's precisely what the CAP theorem tries to explain. CAP stands for consistency, availability, and partition tolerance. Consistency means that all nodes of the data store reflect exactly the same data at the same time. In our case, we had different values of inventory in different nodes. Therefore, we can safely say that our database cluster is not consistent. Availability means that all the nodes of the data must return a response without the guarantee that the data will be the latest, which means that the nodes will respond, but it may happen that stale data is returned. In our case, all of our nodes were returning data, but the read replicas did not return the latest, which means our database cluster was available. Partition tolerance means that all nodes of the data store must continue to function despite a network partition. A network partition simply means that the networking among the nodes is delayed or broken. This is not to be confused with data partition, which is an altogether different concept. In our case, we did see that our system continued to function despite network issues among the nodes. The data returned from some of the nodes was stale, but it was still functioning, meaning our database cluster was partition tolerant. Now, CAP theorem states that a distributed data store can only guarantee 2 out of these 3 properties. Why? Let's think about it. When the first user placed the order, the write could successfully complete without caring about the updates on the read replicas. So if we had a network partition, that is, 1 or more read replicas were not connected, the system remained available and the transaction could go through, meaning partition tolerance and availability was guaranteed, but at the expense of consistency. However, if we change this behavior and set the database cluster setting to fully synchronous and the same user place the order of 2 units, the user will endlessly see a loading spinner because 1 or more of the read replicas are not reachable. Ultimately, it will be timed out and the operation must be cancelled, keeping the inventory intact as 2 across all the nodes. Thus, prioritizing consistency but at the cost of availability because the transaction could not successfully go through. Please note that in a practical sense, the operation may be retried via idempotence or the inventory is re-released programmatically behind the scenes to ensure strong consistency. So we could clearly see that in a distributed data store, if we prioritize partition tolerance, we can only guarantee either consistency or availability. And that's precisely the CAP theorem. In a system design interview, you will have to make this choice, and it's never wise to ask the interviewer what that choice should be. It's your call to explain what you're choosing and the consequences of your choice. Which brings us to the point, how do we really make that choice? If you're talking about systems like ticket booking, inventory on e-commerce websites, booking a cab via Uber, consistency should usually be preferred. so that in case of a network partition, it would probably be wise to compromise on write availability to favor consistency. For example, it's better to fail an Uber booking rather than showing cabs which are already booked. However, if we're talking about browse and search of products on e-commerce websites, uploading videos on YouTube, uploading a photo or a story on Instagram, availability should usually be preferred. What this would mean is that if a new photo is uploaded on Instagram and there happens to be a network partition, it's important that our write goes through despite that. A consequence of this approach could be that a few users may not be able to see your photo immediately. And that's a perfectly acceptable trade-off where we prioritize availability but compromise consistency in case we have a network partition. An important point to be noted here is that as long as the network partition is working fine, you can always satisfy both consistency and availability. Since a network partition is hard to control, the choice between consistency and availability stands as a contingency plan. Now, this consistency is completely different from the consistency in ACID transactions. How? Well, that's a topic for our next video. See you there. Bis dann.